Hello everyone. We will start with what layout optimization really means. Think of it as arranging all the physical elements of a factory and your machines, workstations, tools, and material routes in a way that everything flows smoothly. Okay, the goal is to reduce wasted time, motion, and space. When this is done well, you can see big jumps in productivity without even buying new equipment. It's more about how you organize what you already have. Okay, now if you look at the first diagram here on the left, you will see a poor layout. Machines are placed randomly M1, M2, M3, M4, M5, and materials travel in a scattered path. This means longer travel distances, higher handling time, and more confusion for workers. On the right, in optimized layout, notice how machines are lined up: M1, M2, M3, M4, M5. The material moves in a straight line, shorter routes, fewer delays, and better space use. It's simple but powerful. So, layout optimization is basically about making sure that materials, people, and information move the shortest, cleanest way possible from start to finish. That's how you build efficiency right into the design of the workspace. Now, let's go over the four main principles that guide layout optimization. First, minimize movement. Every extra step, whether it's a person walking or forklift driving, adds cost and time. Reducing total travel distance means faster operations and less fatigue. Second, flow efficiency. You want equipment and processes arranged so that work moves forward naturally. No backtracking, no unnecessary crossovers. When flow is efficient, you reduce congestion and delays. Third, space utilization. Here the focus is on using every square foot wisely. That means, doesn't mean cramming everything together. It means using space productively while keeping safety clearances and flexibility for changes. Flexibility design here. Factories rarely stay the same for long. Product demand shifts, batch sizes change, and new equipment arrives. A good layout can adapt to those changes without tearing down walls or halting production. And why does all of this matter? Because layout directly affects performance. Poorly designed layouts can waste up to 15% of total production time just on unnecessary movement. That's a huge loss. An optimized layout can cut material handling costs by 30 to 50%. That's not theory, those are numbers seen in real facilities. Okay, when you arrange space properly, communication between workers improves and that reduces errors and rework. Plus, when the flow is logical, it supports lean manufacturing and continuous improvement. Workers are not jumping into each other, materials arrive on time, and the system feels balanced. And of course, a well-planned environment is safer and more satisfying to work in. People tend to perform better in organized spaces. Yes, let's continue. Alright, let's look at the main layout types. What are they? Each one fits a certain kind of production environment. Start with the process layout here. You group similar machines together, like all drilling machines in one area, all milling machines in another, and so on. This is great for low volume, high variety production. You get flexibility to handle different jobs, but the trade-off is longer material travel and more complex routing. Next, the product layout. Here machines are arranged in the exact sequence of operations for a product. And think of an assembly line. For example, OP1, OP2, and so on. This setup gives you high efficiency and continuous flow, perfect for high volume, low variety production. But flexibility is limited. You can't change product types easily without reconfiguring the line. And look at this third cellular layout. This one combines the best of both worlds. Equipment is grouped into small cells, each dedicated to a part family or product group. It reduces travel distance while keeping some flexibility. For example, if you produce different but related parts, you can adjust within the cell without disrupting the whole factory. And here, the fixed position layout. Here the product stays still and workers, tools and materials move around it. This makes sense for large items like aircraft or ships, where moving the product itself would be impractical. The downside is it requires careful coordination of resources because everything has to come to the product instead of the other way around. Okay, and that's okay. We talk about it. And notice the two boxes at the bottom of here. The traditional approach to selecting layouts was mostly based on habit, just placing machines by type or what was done before. The optimized approach is data-driven. You analyze product families, volumes, and flow patterns and align your design with business goals. That's how you move from a functional layout to a truly efficient one. Yes, let's continue. Alright, now let's move on to the tools used to design and analyze layouts. What are they? These helps us move from guesswork to evidence-based planning, and here from to chart. This is a matrix that shows how materials move between departments or workstations. Each cell tells you how many trips or how much material goes from one place to another. For instance, if you see a high number between cutting and assembly, it means there is a lot of interaction there, so those two areas should be close to each other. The goal is to identify high traffic routes and minimize unnecessary travel. Then there is the activity relationships uh, or activity relationship diagram. This is more visual. It shows how close different areas should be located based on things like communication, noise, vibration, or workflow. Lines between departments can indicate strength of relationships, often coded by letters like A for absolutely necessary, E for especially important, and so on. Okay, next here, space relationship diagram. You take those activity relationships and convert them into actual spatial blocks. Each block represents a department sized by how much space it needs. Connections between them show how strong their relationship is. And this diagram is likely the early sketch of your layout before finalizing exact placements. And here we have material flow simulation. What is that? Or here, look at this. This uses computer models to test how a proposed layout performs before you actually build it. You can run different scenarios, maybe change the machine order, adjust space, or modify flow direction, and see the impact on throughput, utilization, work in progress, and lead time. This helps catch bottlenecks early and fine-tune efficiency before any physical change happens. Alright, here distance reduction target, and here estimated annual savings. It starts from 20% and goes to 70% and watch the changes. Okay. Alright, and now let's look at how layout optimization actually gets implemented in practice. You can see in the diagram here the process follows a structured roadmap from data collection to implementation, spread roughly across 18 weeks. This timeline is not rigid, of course. It depends on the scale of your operation, but it gives a realistic rhythm for how a full project unfolds. And let's look at this here or here. Look at the very first block is the data collection, which usually takes about 2 weeks, and of course it can change. During this period, you gather everything you can about the current system, production volumes, how parts move through the plant, the material handling methods, equipment dimensions, and even future growth projections. Basically, this is where you build the factual foundation. Without accurate data here, every later decision is built on the shaky ground. Okay, and here look at this analysis stage, which often takes around 3 weeks. Just example. Now you start for looking for patterns. Where are the bottlenecks? How long are travel distances? Which areas see congestion? And where do people or materials cross paths unnecessarily? By the end of this stage, you have got a clear view of your current state and you know what needs fixing. And after that, we move into design. Here's we, here's I'm saying where creative engineering comes in. You take all that analytical input and start sketching multiple layout options. You are not just rearranging machines, you are thinking about flow direction, safety zones, storage, and maintenance access. You test ideas and refine them, looking for that balance between efficiency and practicality. Okay, once a few alternatives are ready, you enter the evaluation phase. This usually takes a couple of weeks. You measure each design against criteria like cost, flexibility, and ease of implementation. You might even use simulation software to see how the design performs under real operating conditions. Then detailed planning kicks in. This takes about 3 weeks and it's all about precision. You prepare final drawings, coordinate utility relocations, plan move schedules, and define responsibilities for every department involved. And finally comes the implementation phase. And here you execute the move, test the new setup, and adjust as needed. The key is to do this with minimal disruption to production, ideally during scheduled downtime. By the time this phase wraps up, the new layout is not just on paper, it's up and running. Okay, everything is done, and when it comes to execution, even the best design can fail without proper planning. That's why there are a few success factors to keep in mind. What are they? First, involve operators and supervisors early. They know the workflow better than anyone and often spot practical issues that designers overlook. And second, plan the move during low volume or scheduled downtime that minimizes disruption to daily operations. And what is third? Stage equipment and utilities in advance so that when installation starts, there is no waiting around. And you will also want to create detailed move plans with clearly defined responsibilities. Everyone should know what they are doing and when. Before going full scale, test a new layout with pilot runs. Small production tries to confirm everything functions as intended. This approach keeps risk low and builds confidence before you commit to full transition. Yes, that page is also done. Alright, optimization part is here. This is one of the most impactful parts of layout design. Essentially, we are trying to make sure materials move the shortest possible distance with no backtracking or unnecessary intersections. Because every extra foot of travel means wasted time, energy, and money. And on the left side of the diagram, you can see a complex flow. It has multiple crossovers and even backtracking. The total distance here is, what is that? About 850 feet with a handling time of 18 minutes. On the right, there is a straight line flow. Materials move sequentially 1, 2, 3, 4, 5, 6 with no detours. That cuts total travel distance down to around 320 feet and handling time to 7 minutes. And that's a 62% reduction in material handling effort. And now, when you multiply that improvement across hundreds or thousands of units produced per day, the savings become enormous. Less movement also means less congestion, lower accident risk, and smoother operations overall. Okay, and principles, let's look at what are they. So, the first one is straight line flow. Keep operations arranged in a sequence that follows the natural order of processing. This avoids turns and backtracking, which add confusion and delay. Second, minimize crossovers. Every time two material paths intersect, you risk congestion and accidents. So the idea is to create one-way movement patterns wherever possible. Third, point of usage, point of use storage. And this simply means keeping materials close to where they will be used. For instance, placing bolts right next to the assembly station instead of across the room. And that small change saves a lot of handling time. And finally, unidirectional flow. Materials should move in one direction from raw material to finished product without looping back. It makes tracking easier and prevents interference between operations. Alright, you can see an example comparison and we have a slider. So what's happening here? Before optimization, the average travel distance was, let's say, 800, right? Just make it, anyway, distance was 850 feet per unit with a handling time of 18 minutes and an annual handling cost of about $51,000. After optimization, those numbers drop dramatically. Travel distance goes down to 320 feet, handling time to 7 minutes, and annual cost to roughly $19,380. That's a clear demonstration of how design decisions directly affect cost and efficiency. Here are other values. Okay, let's continue. And let's look at cellular manufacturing here. This approach blends the flexibility of a process layout with the efficiency of a product layout. The idea is to group machines into cells where each cell handles a family of similar parts that share common processing steps. If you look at the diagram, you will see a cell containing a lathe, mill, drill, grind, inspect, and pack station, all arranged so that one operator can easily walk between them. The flow starts from raw material here and ends with finished goods. Okay, right here green, and here the dot, um, what is that? That orange line shows the operator's working path, and you can see it's short and efficient, right? Like that. And this design has multiple benefits. What are they? Lead time can drop by around 65% because materials don't wait in queues between departments. Space savings can reach 35% because everything is arranged compactly. Quality improves by roughly 20% due to immediate feedback. Issues are caught and fixed on the spot, and because work happens in small batches, you get single piece flow and reduced work in progress inventory. So how about the methodology? You start by analyzing your product families. That means grouping parts that have similar shapes, sizes, or process sequences, usually with 70 to 80% similarity. This keeps cell utilization balanced and prevents overcomplication. And next, calculate the equipment requirements based on production volume and takt time. That's available production time divided by customer demand. Once you know how many machines and operators you need, you arrange them in a U shape or L shape. Okay, and that's okay. These shapes are popular because they minimize walking distance and make it easier for operators to manage multiple machines. And when the cell is up and running, you measure its performance using four main metrics. Lead time, you aim for a 60 to 75% reduction by cutting out queue time and batch delays. Space efficiency, you target about 30 to 40% reduction in space usage through compact arrangement and less storage of work in progress items. Quality, you look for a 15 to 25% boost in first pass yield because problems are caught immediately. At productivity, this usually increases by 20 to 35% per operator thanks to simplified flow and reduced motion. And what are best practices? Let's start. Design for clear visibility. Operators should easily see work status and any issues that arise. Place code inspection right inside the cell so feedback is immediate. Keep material delivery and finished goods pickup near the cell perimeter for convenience. And try to size each cell for 3 to 5 operators. That makes it easier to balance workloads and rotate tasks. And leave some space for continuous improvement activities like problem-solving boards or quick stand-up meetings, and of course built-in flexibility for future growth because production demands change and your layout should be ready to change with them. Yes, and okay, what is next? Look at this design is here. So here, when we talk about warehouse design, what we are really talking about is how to make movement and good access as smooth and efficient as possible. A good warehouse layout can make a massive difference in how fast you fulfill orders and how accurately you track inventory. So if you look at the layout diagram on the screen, you will notice that it's divided into different zones. Receiving, inspection, and storage for A, B, and C items, the picking area, packaging or packing, and shipping. Now, those A, B, and C labels come from what's called an ABC analysis. It is a simple way to sort items by how often they move. A items are your fast movers, the ones you need all the time. They sit right in what's marked here as the golden zone here, close to shipping and picking, so workers don't waste time walking back and forth. And B items move less often, and C items are your slow movers, so they are placed farther away. This design helps balance two key things. What are they? Storage density, meaning how much you can fit, and accessibility, how quickly you can reach it. Now think of this layout like city planning. The golden zone is the downtown area, everything happens fast there. The Z item zone is more like the suburbs, slower pace, more space. And when you plan a warehouse layout, you are really deciding what should be downtown and what can live further out. Okay, next we get into the storage zone design and look at this. Here's where the warehouse becomes more than just boxes on shelves. Each zone, I mean receiving, storage, picking, and shipping, has its own logic. The receiving zone is where goods first enter. You design it for quick unloading, inspection, and put away. The storage zones, on the other hand, focus on organizing everything by velocity, size, or handling needs. You can see how that makes it easier to maintain both density and easy access. And there is a picking area. That's where most time is usually lost. Every step a picker takes is time and cost. So this area is optimized for speed. Paths should be short, routes logical, and materials positioned smartly. And the shipping zone handles staging and consolidation before orders go out. It is the last checkpoint to make sure everything is correct. And what's happening here? Slotting optimization. Basically, this means giving every product its best parking spot. Think of it like organizing your fridge. The milk and eggs go where you can grab them easily because you use them often, while that jar of pickles you open once a month can stay in the back. In warehouses, we assign CQs based on velocity, cube size, and order patterns. Products that are often ordered together should be physically close to reduce travel distance. Okay, and what are the here metrics, interactive parts? So anyway, what's the impact of doing this right? Looking at the numbers here, and the system shows a daily order volume and make it 350 orders. And when we switch from random slotting to optimized slotting, the average peak path drops from the 420 feet to just 185 feet per order. That's more than a 50% reduction. Orders per hour jump from 12.5 to 21, and space utilization climbs from 78% to 87%. All these gains boil down to one main goal: reducing wasted motion. You can see at the top that the average minutes per order line is around 2 point here 2.5, right? And the target is under 3 minutes. That means the process is performing within an ideal range. And when you think about it, every unnecessary step in a warehouse adds up over the day. If a picker walks even 10 feet extra per order, multiply that by hundreds of orders. The result is hours of wasted time. Slotting optimization solves exactly that. Okay, and last page is here. Anyway, and let's talk about the continuous improvement and adaptation. Layout optimization is not a one-time thing you do and target. Markets change, demand changes, products come and go, so the layout has to keep up. The circular diagram here shows a continuous improvement cycle. Monitor metrics, identify opportunities, analyze the root cause, implement change, and validate results. And here's how it works in real life. You start by tracking performance. Maybe you notice peak times are creeping up. That's your signal to identify where the bottleneck is. Then you dig into why it's happening. Maybe storage zones got unbalanced or the product mix shifted. Once you understand the cause, you make adjustments like reslotting some CQs or rearranging a few racks. After that, you check whether those changes actually worked. Then the cycle starts again. It is like tuning an instrument. Small, constant adjustments keep everything in harmony. Okay, the next section shows how to track performance, and you will see four main practices here. What are they? Quarterly reviews, layout kaizen, simulation updates, and scalability planning. So quarterly reviews are about looking for changes in your product mix and spotting new issues. Layout kaizen means quick improvement sessions, short focused tweaks that fix specific problems without major downtime. Simulation updates are important too. They use virtual models to test layout changes before you make them real, and scalability planning helps make sure the layout can expand easily as you grow. And right under that, you can see adaptation triggers. These are basically the alarms that tell you it's time to recheck your layout. For instance, if your product mix changes by more than 20% or you add new products with totally different handling needs, or your overall volume shifts by more than 30% of capacity, you know it's time to adjust. Another warning sign is when space utilization drops below 75% or shoots above 95%. Both extremes mean something's off. Either you are wasting space or you are packed too tight. Okay, and last part. Take a look at the review frequency section. Here it shows allowed reviews every 6 months and typical performance improvement ranging between 15 and 25% after each optimization. That's a pretty realistic gain when you continuously refine layout efficiency and material flow. Then we have the part about building layout optimization capability. This is about developing internal expertise, so you don't rely entirely on consultants or one-time fixes. The goal is to train people on analysis tools, simulation software, and standardized evaluation methods. Cross-functional teams bring the results because they mix analytical insight with practical shop floor knowledge. Okay, and that's all for this lesson. Thank you for listening.